This is a quick revision of Topic 8, AQA GCSE Chemistry, Chemical Analysis. A pure substance is a single element or a compound not mixed with any other substance. You can test the purity of your substance by measuring the melting or boiling point of your substance. This is because pure substances will melt and boil at specific temperatures. So to test for the purity, you can measure the melting or boiling point of your sample and then compare the melting and boiling point with the ones that have been published in a data book for pure substances. The closer the measured melting or boiling point to the actual value, the purer the substance. Impurities will tend to decrease the melting point, and then that means that your sample will have a lower melting point and also will melt over a range of temperatures. Impurities will also increase the boiling point, and your sample will boil over a range of temperatures. Formulations. Formulation is a mixture that has been designed as a useful product. Each component in a formulation is present in a measured quantity that contributes to the properties of the formulation so it can meet its required function. So each component in a formulation will serve a certain purpose for that particular formulation. Formulations are made by mixing the component in carefully measured quantities to ensure that the product has the required properties. Some examples include fuel, cleaning agents, paints, medicines, alloys, fertilizers, and food. Chromatography is a separation technique. In chromatography, we have a mobile phase and a stationary phase. The mobile phase is a solvent that will carry soluble components of the mixture, and the greater the solubility of the component, the faster it moves through the stationary phase. Stationary phase, however, will slow the movement of the component attracted to it. And the stronger the interaction, the slower the components will move through the stationary phase. The whole separation process is a result of the balance between the component interaction with the stationary phase and the mobile phase. Example of chromatography is the paper chromatography. Paper chromatography is an analytical technique that can be used to separate components of a mixture by depending on their relative speed in a solvent as it's spread through the paper. So the mobile phase here is going to be a solvent and the stationary phase here is going to be a paper. Some of the mixture that can be separated using paper chromatography is the pigments, different pigments in a colored substance. In paper chromatography, what we do, we get the stationary phase, which is the paper, and then we need to draw the starting line. The starting line here is going to be drawn using a pencil, not a pen, because the pen can dissolve and has pigments and can dissolve in the solvent and can travel through the paper. And then you put your different spots on the starting line. You have a beaker, you put the mobile phase in the beaker, and then when you do so, you will put your paper inside the beaker and make sure that the starting line is above the level of your solvent. Need to cover the beaker to make sure that the solvent don't escape, and then you will leave the solvent, the paper in the solvent, where the solvent will travel through the paper, carrying the different spots and separating the different component of the mixture, as each component in the mixture will have different solubility in the solvent and will travel a different distance. When we do paper chromatography, we can measure the RF value. The RF value is the distance moved by the spot over the distance moved by the solvent. When you do paper chromatography, make sure that the solvent doesn't overflow on your paper, meaning the solvent only travels uh, below the top level of your paper. As you do so, you take the paper out and then you need to mark where the solvent traveled to the point where the solvent traveled. This is going to be called the solvent front. And then you measure the RF value by measuring the distance moved by the spot. This is the distance between the starting line and the center of your spot. And then the distance moved by the solvent is the distance between the starting line and the solvent front. RF values can be used to identify each component. The RF values can differ depending on the solvent we used because different substances will have different solubilities in different solvents. The RF value can be used to identify compounds as well because the substances contained within a mixture, one is compared to a reference value. So each component in a mixture has a different RF value and can be compared to a reference value. Substance creates a series of spots, and each spot will represent one specific substance if this is a mixture. If it's a pure substance, then you will only get one spot. Testing for gases. You can test for hydrogen by using a burning splint and hold it at the open end of a test tube of the gas. If it creates a squeaky pop sound, then this is hydrogen. To test for oxygen, you can use a glowing splint and insert it in a test tube of the gas. If the splint relights, then this is oxygen. To test for carbon dioxide, you can bubble the gas through lime water, which is a clear solution of calcium hydroxide. As carbon dioxide bubbles through the lime water will turn milky or cloudy. This is due to the formation of calcium carbonate. To test for chlorine, you can use damp litmus paper, and the damp litmus paper, if it's put in the chlorine gas, the litmus paper will be bleached and will turn white. Testing for ions. You can test for cations, which are the positive ion of the compound. First of all, let's test for different metals. You can use the flame test to test for different metals because different metals, when put in a flame, they will lead to the coloration of the flame with specific colors. So lithium will turn the flame into crimson. Sodium will turn it into yellow, potassium will give you a lilac color, calcium will give orange-red, and copper will give a green color. We can also test for metals by using sodium hydroxide. Some metals form colored precipitate with sodium hydroxide. So if your substance contains one of the following metals, calcium, aluminium, or magnesium, and you add your substance to sodium hydroxide solution, they will give you white precipitate. Aluminium can even be more easily distinguished because if you add excess of the aluminium, the solution will turn clear again, so the precipitate will redissolve. Copper 2 plus ion will give you a blue precipitate with sodium hydroxide. Iron 2 plus will give you a green precipitate, and iron 3 plus will give you a brown precipitate. Testing for anions. Anions are the negatively charged ion of your compounds. The anions we can test for are carbonate. So you can test for the presence of carbonate anions by using dilute acid. So if your substance contains carbonate anions and then you add it to a dilute acid, then carbon dioxide will be formed, which is going to be observed as bubbling, but also you need to test for carbon dioxide by using the lime water in the same way as we tested for carbon dioxide before, where lime water will turn cloudy. We can also test for halides, and halides are chloride, bromide, and iodide ion. First, we need to add dilute nitric acid to our substance, and then we will add silver nitrate solution. Different halides will give different colored precipitate with silver nitrite due to the formation of insoluble silver halides. So chloride will give a white precipitate of silver chloride. Bromide will give a creamy precipitate of silver bromide, and iodide will give a yellow precipitate of silver iodide. We can also test for sulfate. Sulfate can be tested for by the formation of insoluble barium sulfate. So first we add dilute hydrochloric acid to our solution, and then we're going to add barium chloride solution. A white precipitate will be formed when sulfate ions are in the solution due to the formation of insoluble barium sulfate. We can also use instrumental method to test for metal ions. Generally speaking, elements and compounds can be tested for using instrumental techniques, not just the chemical test. Instrumental techniques are better than the chemical test because they are more accurate, more sensitive, and they are rapid. So flame emission spectroscopy is a test that we can use or is a technique, instrumental technique that we can use to test for the presence of elements. So every metal ion will give a characteristic line spectrum when put in a flame. What happens is that if you put your element or your compound in the flame and it has a certain metal or a center element, then each metal will have a different line spectrum because the element will have electrons that are in a specific energy level. When they are put in the flame, the energy level the electrons will absorb the energy from the flame, and the electrons will be promoted or excited from this energy level to a higher energy level. So the electrons will be in a higher energy level. Then these electrons are going to lose this energy, and then they will go back to their normal energy level. They're going to lose the energy in the form of light. These lights can be passed through a spectroscope, which can analyze it and give you the respective wavelengths of these lights, and that will generate the line spectrum specific for each element. Each element will give a specific line spectrum because the nature of these lines will depend on the charge on the metal and also will depend on the electronic structure. No two elements will have the same electronic structure and the same charge, so each element will give you a completely different line spectrum. Also, the intensity of the colors can give you indication of the amount of the element in the mixture or the amount of the element in your sample, so it can be used quantitatively as well. Flame emission spectroscopy can work for mixtures as well, and it can be used to identify different ions in a mixture. So it's more useful than flame test because flame test can be only used if you have only one element. So let's have an example for that. If you have a mixture of two different elements and you want to test for that, the line spectrum that will be produced will be a mixture of the line spectra of these two elements. So if you have a mixture of hydrogen and sodium, you can compare it to the published known line spectrum for that specific element, and you can find that the line spectrum of the mixture is a mixture of the different lines in the pure substances for these two elements.